All right, let's talk about something that's probably bent your brain into a pretzel at some point, the fourth dimension. We hear the term thrown around all the time in science fiction, but what is it really?
I mean, it's a great question, right? We all learn about length, width, and depth in school. Nice, neat, spatial directions you can actually point to. And then, completely out of left field, they tell you the fourth dimension is time. It just feels like it doesn't belong. Why is it the odd one out? Well, let's actually figure this out. So here's the game plan. We're going to break this down piece by piece. First, we'll get to the bottom of why time feels so weird by changing how we define a key term. Then we'll build up to 4D using nothing but geometry, and you'll get to meet a mind-bending shape called a tesseract. After that, we'll see how physics uses spacetime, and finally, we'll pull back the curtain on what dimensions really are.
Okay, so let's kick things off by making sure we're all on the same page about what a dimension even is, because our everyday understanding of it is, frankly, a little incomplete.
A dimension isn't just a direction you can point in. In the worlds of physics and math, it's something way more fundamental. It's any variable, any coordinate that a model needs to fully describe something. Think about it like this. If you want to meet up with a friend, you need 3 bits of info just to know where to go, like which floor of a building and where you are in the room. But even with all that, you're still missing one crucial variable to make sure you both actually meet. You need to know when. And that right there is your fourth coordinate.
So, a dimension is just a necessary piece of information. Got it. But let's put time on the back burner for just a minute and ask a different question. What would a fourth spatial dimension even look like? We can actually get a pretty good feel for it just by building one from the ground up.
Let's start with the absolute basics, a zero-dimensional point. It has no size, no anything. Now, imagine dragging that point in a brand new direction. Boom, you get a one-dimensional line. Now take that whole line and drag it in a second direction, one that's perfectly perpendicular to the first. You've just created a two-dimensional square. You see the pattern? So take that square, drag it into a third perpendicular direction, and you get our familiar three-dimensional cube.
Okay, so let's just follow that logic to its crazy conclusion. What happens if we could take our entire 3D cube and drag it into a new fourth direction, one that is perfectly perpendicular to length, width, and depth all at the same time? And the answer is a shape that exists purely in the beautiful language of mathematics, the tesseract. It's the four-dimensional version of a cube, and sometimes people call it a hypercube. Now think about how it's built. A 1D line is bounded by 0D points at its ends. A 2D square is bounded by 1D lines. A 3D cube is bounded by 2D squares. So, if we just follow that pattern, a 4D tesseract is bounded by, you guessed it, 3D cubes. And it's bounded by 8 of them, all meeting at perfect right angles in 4D space. Yeah, try not to think about that too hard.
And you can really see the mathematical beauty of it all laid out here. Just look at the vertices, the corners. The number doubles with each dimension. 2, then 4, then 8, then 16. The pattern holds perfectly for the number of edges, for the square faces, and now for these 3D cells, which are the cubes that make up the tesseract's boundary. It all just fits.
So how in the world are we supposed to actually see this thing? Well, the short answer is we can't, not directly anyway. But just like a 3D object, like your hand, can cast a flat 2D shadow on the wall, a 4D tesseract can cast a 3D shadow. So those mesmerizing animations you've probably seen of a cube folding in on itself, that's really just a 3D projection. It's the tesseract's shadow shifting and turning in our world.
Okay, so that was pure geometry, a perfectly valid model with 4 spatial dimensions. But here's the thing. That's not the model physicists like Albert Einstein used to describe our actual universe. For that, they use the very real concept of spacetime.
I love this quote because it's such a simple, elegant way to get a feel for this relationship, right? If 2 fireworks go off at the exact same instant, but in different parts of the sky, they are separated by space. But if 2 fireworks go off in the exact same spot, one after the other, they're separated by time. Space and time are just 2 inseparable coordinates for an event.
So in the model of relativity, our universe is a 4-dimensional thing. But it's not the 4 spatial dimensions of a tesseract. No, it's 3 dimensions of space plus 1 dimension of time. If you want to pinpoint any event that has ever happened, from the Big Bang to you blinking your eyes just now, you absolutely need all 4 coordinates. the where, x, y, and z, and the when, t. And this is where it all comes together. This is the big reveal. We've looked at a geometric model with 4 spatial dimensions, and a physics model with 3 of space and 1 of time. So what are dimensions, really? They're the tools we use to build our models of reality.
The math that runs these models tells the entire story. On the left, you've got the distance formula in a 4D spatial world. It's basically just the Pythagorean theorem with an extra piece. But on the right, that's the formula for the interval between 2 events in space-time. Now look really, really closely. Do you spot the difference? It's that tiny little minus sign in front of the t.
That minus sign, that is the answer to our original question. It's not just some random choice someone made, it's baked into the fundamental mathematics of our universe. That single negative sign is what makes time so weird and different from space. It's the mathematical reason we can move back and forth in space, but we're all stuck on a one-way trip through time. And this brings us to the ultimate takeaway. The number of dimensions you're working with depends entirely on what you're trying to describe. For everyday geometry, 3 is usually enough. For Einstein's relativity, you need 4. For something like string theory, the model needs 10. And get this, if you want to model a simple box of gas, to track the position and momentum of every single particle in there, your model needs a mind-blowing 6 times 10 to the 23rd dimensions.
So you see, the 4th dimension isn't just time. It can be time, or it can be another spatial direction, all depending on the model you're building. And that, of course, opens the door to some seriously wild ideas. Some theories propose a 5th dimension that describes a whole landscape of possibilities, alternate timelines branching off from our own. Which leaves us with one last thought to chew on. If all those potential paths actually exist, is what we call free will just our consciousness choosing and navigating a route through that 5-dimensional space?